Welcome everyone again, and thank you for joining. My name is Shtub, and I'm head of training at ScyllaDB. I am a software engineer. I'm based in Israel. I've been with the company for almost 7 years. And at ScyllaDB, we develop a database software, NoSQL, which I will talk about in just a bit. As you can see, this entire session is live. It's not pre-recorded. I would like to make it as interactive as possible. So I'm sharing one monitor, but I'm also keeping an eye on the chat window. So tell me if you have questions, if I'm going too fast or too slow, and so on. Okay, so my plan for today is to talk about an overview of NoSQL in general, and specifically ScyllaDB. Then I will show you a quick hands-on lab, just how easy it is to get up and running. After that, I will talk about the architecture, basic data modeling in another lab, partitions and keys, and if we have time, I'll talk about drivers. Now, as a general side note, I'm going to be using ScyllaDB as an example, but the concepts that I'm going to be covering today are relevant for other databases, NoSQL databases to be precise as well, namely Apache Cassandra, Amazon DynamoDB, as well as some others. Okay, so I'll be using ScyllaDB as an example. The architecture and many other concepts are relevant for other NoSQL databases as well. Another side note is that we will be sending you an email with the slides and the links to the labs, so you don't have to worry about, I don't know, writing things down or taking photos of anything. We'll send you the material. Okay, so an overview of ScyllaDB. And another side note is that all this material is covered in Scylla University. And Scylla University is a website, university.scylladb.com, where we have lots of courses, hands-on labs, videos, and it's completely free. You just create a user and you can start learning. So that's a useful resource. And another one is documentation that goes more in depth into different procedures, commands, and so on. I want to talk about NoSQL databases in general. But before I do that, maybe if you can just write in the chat window, are you familiar with NoSQL databases? Or should I also explain what that is? If you could just quickly write in the chat window. Do you know what NoSQL databases are? Or should I quickly talk about that as well? So again, the question is, should I explain what NoSQL databases are, or do you already know what that is? If you can quickly type in the chat window. Okay, so let me, I see your answers. Let me start with maybe an overview of NoSQL. So historically, databases started with SQL or relational databases. And think about 50 years ago, even more, there was a limited amount of storage. Think about a bank, and the bank had a big room, typically in the basement, and there was one big computer, and that had the database. And all the data was stored on that computer, and that worked for some years. But in the last 20 or maybe 30 years or so, the amount of data grew exponentially, together with the need for serving data from different locations. So users were located geographically in different areas, and having all the data on one computer didn't really work. It doesn't scale, it has its limits, and NoSQL databases were developed. NoSQL databases, well, it's a bit of a weird definition because it's not SQL, which means there are many types of NoSQL databases, and in this slide, I'll talk about a few and give some examples of different families of NoSQL databases. So I'll start with the most simple in terms of the data model, and that would be a key value database. And for example, there are many, but for example, you can think about Redis, that's a famous one. And just as simple as it sounds, we have a key and we have a value. That's how easy it is to get the data. We don't have any concept of rows and columns and joins and anything complicated like that. And for many use cases, this is good enough. And it's very simple. So it works well, it works fast, and it's simple. Next, in terms of complexity of the data model, are document databases. Some more well-known examples are MongoDB and Couchbase. And here we store our data as documents. Think about structured data such as JSON or XML files. Okay, so there's some kind of hierarchy, and this is how data is stored. Next, we have wide column databases, and this is where I'm going to focus on today. And here some famous examples are Apache Cassandra, Amazon DynamoDB, and also ScyllaDB. And wide columns, you can think about them as a list with tables with rows and columns. Okay, so you have rows and columns in a table, and you can do different operations. And the schema is more flexible than in SQL databases, okay? There are some things that cannot be done. There are some limitations, like joins. However, we get a more flexible schema. Last in this slide, we have graph databases, and some examples are Neo4j and Janus Graph. And this makes sense if, say, we're working with graphical, say, maps or other geospatial data, and we want to model our data as edges and vertices. Okay, so these are some examples. And again, we're going to focus on wide column databases. So there's a question about Firebase Firestore, and I'm not really familiar with that database. So the answer is I don't know. Okay, so a few words about ScyllaDB. ScyllaDB was developed originally as a rewrite of Apache Cassandra. Apache Cassandra is a very well-known and highly used database. However, it's written in Java, and it has a lot of different issues regarding performance and maintainability. So ScyllaDB around 10 years ago was developed as a rewrite of Apache Cassandra with C++ in a different architecture. That's how we got started. And now we have some famous companies or well-known companies that use ScyllaDB. Some of them you're probably familiar with, and they are from different industries. And it's out of scope to talk about specific use cases, but if you're interested, you can look at our website, and there are different use cases from ad tech, from financials, from cybersecurity, and so on. So what are some of the attributes of NoSQL databases, and specifically ScyllaDB? One of them is high availability. So ScyllaDB, and I'm saying ScyllaDB, but whatever I'm saying is almost always relevant for Apache Cassandra and DynamoDB as well. So the database is distributed. That means that the same database runs on multiple computers, on multiple servers, and these servers don't necessarily live in the same location. So they're spread out possibly across different data centers. And that goes together with high availability. High availability means that our data is always available, even if there is a network failure, even if some of our nodes become unavailable, our data remains available. Okay, there is redundancy, and I'll talk about that in just a bit. Second attribute is scalability. So the system is designed in such a way that allows us to add and remove nodes without any downtime. So say that we're running some kind of e-commerce website and Black Friday is coming up. So we know that we're going to get more traffic in our shop, and our database is going to be serving more requests. We can simply add more servers also called nodes, add more nodes to our database. So say instead of having 3 servers running the database, we can scale it up to 5 nodes. We do that without any downtime. And then the database can serve more requests. And maybe after Black Friday, the traffic is going to go down. So we can scale it down by removing those extra nodes, which of course have an extra cost in terms of hardware resources, networking, and so on. So they're scalable. Next is performance. So the sweet spot for these type of databases are applications that require a large amount of data and very high performance. And when I say performance, I mean high throughput and low latency. So we're talking about millions and even billions operations per second, depending on the need of the application. And we're talking about single-digit millisecond latency. Okay, so they run very, very fast, and they have a very high throughput. And again, that depends on the application and the requirements. Next is low maintenance. So I mentioned that one of the pain points with Cassandra was that it was very hard to maintain, and users were keeping teams just to fine-tune Java's garbage collection and stuff like that. So with ScyllaDB, it's written in C++, there's no garbage collection, and the system auto-tunes itself. And ScyllaDB is a drop-in replacement for both Apache Cassandra and DynamoDB, meaning that if you're using one of these 2 databases, you can simply replace the underlying database to be ScyllaDB without making any changes to your application, and then you get many benefits, including better performance and lower total cost of ownership. Okay, so ScyllaDB offers 2 products. One is Scylla Enterprise, which runs either you can run it on the cloud or you can run it on-prem. The second product, which is becoming more and more popular, is ScyllaDB Cloud, which is our managed database as a service offering. And if you choose that option, so with a few clicks of a button, you can start the cluster, and you don't have to worry about managing the cluster, about upgrades, about backup and repairs, anything of that sort. Security hardening, we take care of that. So you can focus on your core business, which is probably not administrating a database. So those are the 2 options. Okay, I just talked for quite a bit. Quick poll question, if you can answer in the chat window. What's your NoSQL status? So one option is I haven't heard about NoSQL yet. Second option is I've heard about NoSQL, but I haven't used it. And the third option is I'm using NoSQL databases. If you can quickly answer in the chat window. I'll also see that I'm not talking to myself. So again, the question is, what's your status with NoSQL? Is this the first time you hear about it? Maybe you heard about it but haven't used it. Or maybe you're already using some kind of NoSQL database. If you can answer in the chat window, let's take a few seconds so more people can answer. Okay, I appreciate the answers. Thank you. I see some people heard about it but haven't used it yet, while others already used it. Okay, so again, this is a bit out of scope, but just at a very high level, I mentioned better performance. So these are some examples from users that migrated from DynamoDB or Cassandra or Google Bigtable or CockroachDB, and a benchmark of the performance they achieved when migrating to ScyllaDB. So in this one example, comparing to DynamoDB, a user was able to use less hardware. They got 1/5 of the cost, And even though the cost was much lower, they still got way better performance. Okay, you don't have to take my word for it. You can see these benchmarks on our website. Okay, I mentioned high throughput, low latency. So here you can see a demo of running 1 million operations per second with just a few clicks of a button. And you get very high throughput. And you can see in this example, the latency is below 1 millisecond. So it runs very fast. And this dashboard is actually our monitoring dashboard. And hopefully I'll talk about it in a bit. So you can play around with this demo and run it yourself. I'll share the link when I send you an email. Okay, with that, I want to show you a quick hands-on lab. It's very simple, but it shows you how easy it is to get up and running. So you can just see what I'm doing, but you're going to be able to run this lab on your own when I share the link with you. So let me switch to the lab. Okay, so what we're seeing here is a platform called Instruct. And actually what it does is it runs a virtual machine. You can't really see it, but let me show you. This is actually running within a browser. Okay, so this is a browser, there's a link, and you can run the virtual machine and play around with Scylla. No installation or prerequisites or anything of that sort required. So I started, basically I clicked run on this command, and what this did was it ran this command docker run, giving the name of the node and starting Scylla with a specific version. Okay, so I ran that just before I started talking. And what that does is it starts a one node ScyllaDB server running in a Docker container. And next, I'm going to run a command called node tool status. And what this command does is it basically tells me what's the state of my cluster. Okay, so my cluster has just one node, and I can see that this node, this is the IP of the node, and it's up and running. It's ready to serve requests. Okay, now I'm going to connect to the node, and I know I'm talking about stuff that I didn't really explain, but I'm going to explain it in a second. So now I connect to the node with something called the CQL shell. And the CQL shell allows me to basically interact with my newly created cluster. So I'm going to create something that's called a key space. A key space is a container of tables. Remember, we're talking about a wide column database that has rows and columns. And using this newly created key space, I create a table. I call it users. Not very interesting. Let me move this thing. Maybe put it here. Okay, so I created the table. I called it users, and these are the columns in this table. It's user ID, name, and some kind of text. Okay, and I define the primary key to be the user ID. Okay, so nothing very interesting. So far, very straightforward. Column names and their data types. And now that I created my users table, I can insert some rows into the newly created table, like that. And when I read those rows, select star from the table, I can see that those two rows were indeed added to my table. And that's how easy it is to get started. Okay, so let's go back to the slides. Okay, so I showed you how to get up and running with the database, but I talked about different concepts that I didn't really explain. So let's go over those concepts. Okay, I'll talk a bit about the architecture of NoSQL databases and of ScyllaDB. The basic unit of architecture is called a node. A node is simply the ScyllaDB software running on a server, running on a machine. Okay, so that's a node. In ScyllaDB, each node contains a portion of the database content, and all nodes are created equal. Okay, so that means that unlike other databases that have the concept of leader follower or master slave or however other name you want to call it, in ScyllaDB as well as in Apache Cassandra, all nodes are created equal, and that goes together with high availability because there's no single point of failure. Even if one or more nodes go down, the database can still serve requests. Now, nodes work together to serve requests in what's called cluster or a node ring. And in this example, we can see a 5-node cluster, okay? So these 5 nodes, we conceptually think about them as a ring, and they work together to serve requests. Now, in the example that I just showed you, in that small example, we had just a 1-node cluster. That was a demo, and that's fine. But in production, the recommendation or best practice is to have at least 3 nodes, okay? So it's recommended to have at least 3 nodes, and the number of nodes can go all the way to hundreds of nodes working together, and the exact number of nodes depends on your application, on your data size, on your performance requirements, on the topology, data centers, and so on. So that's a cluster. Another important concept is data replication, okay? So in ScyllaDB, data is replicated to different nodes. So the database holds multiple copies of each data, and each piece of data or each copy is held on a different node, okay? It brings me back to high availability, which I keep on mentioning. Because we have copies of the data on different nodes, even if one or more nodes become unavailable or go down for some reason, we can still serve requests. Okay, so data is replicated automatically. As a user, you don't need to replicate the data. However, the number of nodes where data are replicated is determined by something called the replication factor, also abbreviated as RF. Okay, this is quite important. And the replication factor is set per key space. Okay, a key space is a container of tables. So each key space can have multiple tables, and the key space defines different settings for all the tables that are within that key space. And one of the important ones is the replication factor, okay? So in this example, we create a key space, we call it my key space, and we define the replication factor to be 3. What does that mean? It means that if we have, in this example, a 5-node cluster, and we have a replication factor of 3, then when we write data, say this orange cube is a piece of data, that data is going to be copied or replicated to 3 different nodes, node 1, node 2, and node 3 in this example, and so on for other pieces of data. They're all replicated, and each piece of data is stored on a different node. Okay? Now let's understand how that data is replicated. Again, this is something that happens under the hood. The database does that for you. But when we're talking about our data model, it's important to understand how it works under the hood. Okay, so when we write a piece of data to our database, each table has a partition key. A partition key in ScyllaDB and Cassandra and DynamoDB is 1 or more columns, and the database takes the partition key. In this example, it's the pet chip ID, okay, this long UID or GUID, and it performs a partitioner hash function on the data here, on the partition key. And according to the given hash, it knows which nodes are responsible for this piece of data. Okay, so let me repeat that. The database performs a consistent hash function on the partition key value, and according to the given hash, it knows which nodes are responsible for this data. And as you can understand, this happens very fast. So performing the hash function is very fast, either for a read or for a write, and the database immediately knows where the data exists. Okay, next concept is the consistency level. So I talked a lot about availability. It's also important to talk about consistency. And typically there is a trade-off between availability and consistency. In ScyllaDB, we talk about eventual consistency, and the consistency level is another setting that you as the user can define. And consistency level means the number of nodes that must acknowledge a read or a write request. Okay, so now when we perform a query, say a read or a write, we can define the consistency level per that specific operation. Okay, so maybe we have a write, say we write data every second. We are talking about an IoT application. We have some measurements, say we measure the temperature of the room, and every second we write the temperature to the database. In that case, maybe the consistency level for each given write is not that important. So it's not that bad if we miss 1 second, right? Because we're writing the data every second. But maybe our application is performing a read once a day. And for that read, we can set the consistency level to be higher, because for that, we want it to be completely consistent, okay? So some examples of consistency levels are 1, quorum, local quorum, and all. And if I define, say, I have a 3-node cluster, and I define the consistency level for, say, a read operation to be quorum, then what that means is that 2 out of 3 nodes, which is the quorum, must acknowledge this read request. Okay, so even if 1 node out of the 3 nodes is down, 2 out of the 3 are going to respond, and I will still get a successful answer for my query. And of course, there's a trade-off here, because if I set the consistency level to be higher, my data is going to be more consistent, but it's going to be in account of the availability. So if I set it to all, that means that all 3 replica nodes must acknowledge the request. And even if 1 node is down, then my query will fail. Okay, so there's a trade-off here between the consistency and the availability. Okay, I mentioned that the database can run in different locations. It's distributed, and it's also topology aware. What does that mean? It means that the database knows about the topology of where it's running. In this example, we're running the same database, so the same cluster, but it's distributed all over the world. So say we're using 1 data center in the US, 1 in EU, and 1 somewhere in Asia. Why does that make sense? Does anyone know why we would want to do that? Why we would want to use multiple data centers in different geographical areas for the same application? You can write in the chat window if anyone has any idea. So again, the question is, what would be the reason that we would want to have a distributed cluster running across different countries in different geographical reason areas? Anyone have an idea? Okay, so that's correct. There's one answer to get faster queries based on the location of the user, and that's correct. Another answer is high availability and low latency, and that's also correct. Any other ideas? Both of those answers are correct, but I can think of at least one more reason that we would want to do this. Okay, so I'll tell you. first of all, I'll repeat the things that you already said. We're talking again about very highly performant applications, lower single millisecond queries, and just the time it takes for data to say move from America to Asia. If I remember correctly, it's around 100 or 200 milliseconds. So it would make sense to serve a user from, say, the United States from a data center in the United States, just for performance reasons, okay? So one is, like you said, fast query response. The second is high availability. And it's not very common, but it does happen that, say, there's an earthquake or a fire, and an entire data center can become unavailable. And in that case, if we have multiple data centers, we have extra redundancy. And we actually had a case where one of our users, it was somewhere in Europe, maybe Austria, or yeah, I don't remember, maybe Germany. Anyway, there was a data center that went down because of a fire. Our user had another data center and they were still serving requests. And at that time, there was an outage of hundreds of websites that stopped working, but they were still able to run. Yeah, I'm trying to remember the details, but I can't. We have a blog post about it. I think it was a travel website. But anyway, that's an example of why it's useful to have multiple data centers. And another reason might be for regulation reasons. So some jurisdictions, some countries have laws that require that the information of users stay within that geographical area. And by using multiple data centers, we can ensure that all the data of those users stays in that particular geographical area. Okay, let's skip this poll because I have a lot of material to cover. Are there any questions so far before I move on to some data modeling concepts? Any questions, feel free to ask. Okay, and also feel free to ask in the chat window later on if you come up with something. I see there's one question. Somebody's raising their hand. You can just feel free to write in the chat window. That would be the easiest. Okay, so let me move forward and I'll keep an eye on the chat window for questions. So let's talk about basic data modeling, how we model our data in NoSQL databases in general, and specifically in wide column databases, and more specifically in ScyllaDB. So I'm assuming that some of you have a background in SQL or relational databases, and this is a comparison of how data modeling is done with NoSQL databases as compared to relational databases. Okay, so this is an important slide. Typically in relational databases, the way that we model our data is that we first of all think about our data, what type of data we have, the entities, the relationship between the different entities, and we start with that. From that, we derive our model or schema. And finally, when we have that, we think about our queries and about our specific application. Okay, that's how it's in a very high level done with relational databases. In NoSQL, the main difference is that we think about the application at the very beginning. Okay, instead of thinking about it at the very end, we start by thinking about what's our data, but also together with that, what queries we're going to be performing in our application. Okay, once we think about those two things, we can create our schema and the actual data model, the tables, the rows and columns, and so on. Okay, and I'll try to give you an example of this. So the question is, do the regulations also disallow storing of data of one country in another country? So that's completely possible. Again, there are some jurisdictions that have different rules, and the database is just a tool that allows the user to choose how they want to implement it. So it's up to the user if they want to spread the data all over the world, if they want to keep it in a specific country. It's up to the user that uses the database according to the regulations in a given country. Okay, so I'm going to be talking about some concepts in data modeling. I touched on some of them. The first one is key space. So a key space, like I said, is a container. Here in pink, it's a container of tables. It can have one or more tables. Some applications have just one key space. Others, where it might make sense, might have more than one key space. And the key space determines different settings for all the tables that are within that key space. And one important example of such a setting is the replication factor, okay? Which I talked about before. If you remember, it's how many copies do we keep of each piece of data. So within the key space, we have multiple tables. If you remember in the quick wins example, I showed you a very basic table with things like user ID and name, first name, last name, something like that. So the way that we think about the table or the way that it's stored is it has different settings, like the primary key, which I'll talk about in a second. And then we have something called the partition key. Okay, if you remember, the database uses the consistent hash function to partition the data. So it takes the partition key value, performs the consistent hash function, and that's how it knows where the data belongs. So we have the partition key, and then we have either the clustering key and a set of values. Okay, I'll show you another example which better explains how it's structured on the hard drive. So this is a key space. We already saw this example, and this is how we would create a key space. In this example, pets clinic, we define the replication factor to be 3, and we create a table within that key space that has the pet chip ID column, time, and heart rate. For each column, we define the data type for that column, UUID, timestamp, sorry, and integer. And we define the primary key. In this case, it's pet chip ID. Okay. Okay, so in the example that I showed you, we used the CQL shell. What is CQL? CQL stands for the Cassandra Query Language. It's similar to SQL, but also different. So we have different commands for performing create, delete, alter, select, insert, update, and so on. And you can interact with the database using the CQL commands. And the CQL shell is an interactive shell that allows us to interact with the database. And that's what I'm going to be showing you in the example in the hands-on lab. However, keep in mind that in real-world applications, we use drivers, okay? Drivers are available in different languages, pretty much any language that you can think of. And in real-world applications, you can use drivers. There's an entire course in ScyllaDB University about drivers in different languages. Okay, with that, I would like to very quickly show you the data modeling lab. The data modeling lab is longer, it's more elaborate, so I'm just gonna show you the very beginning, and you can run it on your own afterwards. Okay, so in this lab, again, we create a single node cluster by running this command. Again, using Docker, we create a node called node X, same as before. Don't do this in production. Like I said, in production, you need at least 3 nodes. But here we're just playing around with the cluster, so it's fine. I run node tool status. I see that my node is UN, which stands for up and running. And I connect to my node with a CQL shell, and I am ready to perform different commands. Okay, so let's start by creating a key space. Again, this is something that we saw before. And I create a key space. I call it a key example with a replication factor of 1. I'm getting a warning that it's not recommended to use a replication factor of 1 in production, but we already talked about that. And within that key space, I create a table, just like we saw in the slides, with 3 columns: pet chip ID, time, and heart rate. Okay, I define the primary key to be pet chip ID. Okay, so now that I have my table ready, I can insert some data, and I insert just 1 row, and I can read the data. Nothing very interesting here. What happens if I want to add another row, another value, say another heart rate value for the same pet? Okay, so I'm going to insert another row. I'm going to provide the same pet chip ID, but I'm going to provide a different heart rate, 110 instead of 100. So I run this command, and can anyone tell me, please, in the chat window, what do you think will happen when I run this command? Will this succeed? Will it fail? What's going to happen when I run this command? Again, I'm trying to add another heart rate value for the existing pet chip ID. What happens here? Anyone, feel free to guess. So I'll repeat what I did. I added 1 row to my table, and then I wanted to add another heart rate value for the same pet chip ID. Pet chip ID is defined as the partition key. What do you think will happen? So one idea is that it should succeed. And there's a question if the values are in wrong order. I don't think so. So it's pet chip ID is the first one, time is the second one, and heart rate is the third. And another answer is duplicate key succeeds in the same partition. Okay, so let me just show you. When I read the data, I'm going to see that, well, the query succeeded, but it didn't really do what I wanted. So it actually, instead of being a write or an insert, it was an upsert. It updated the previous row, which wasn't really my intention. So it overwrote the previous value of 100, and it changed it to 110, okay? And this, by the way, is the same behavior you would get for Apache Cassandra and DynamoDB. So keep in mind that inserts are actually upserts. They can update the data. And the way to overcome this issue and get the behavior that we want would be to use something called a cluster key. A clustering key, that's how it's called in ScyllaDB and Apache Cassandra. In DynamoDB, it's exactly the same thing, but it's called ordering key, okay? Which is probably a better name, but we use clustering key. And the clustering key, let me show you how it looks like in the slides. Okay, so this is the slide I wanted to show you before. We have partitions, okay? This is pet chip ID or whatever we define as the partition key. And then for each partition, we have key value pairs, okay? So we have time and the heart rate key value pairs. Now, when we added another value, we simply overwrote the previous one. However, when we add clustering keys, then we can have more than one value for a given PetChip ID. And these values will be sorted according to the clustering key. Okay, so here they're sorted according to the time. And you can think about the database and how it very efficiently knows where our data exists, and we can also query according to the clustering key. Okay, if we query only according to the partition key, the partition can be quite large, say, I don't know, 20 gigabytes. And then the database has to just scan all that information to find the data we're looking for. However, if our data is sorted, then if we query according to the clustering key, we can find the data very efficiently. Okay, so let's see how that's done. Okay, so I connected to my node, and using the same key space as before, I create a new table. I get an error. Why is that? Okay, right. So I'm trying to perform a select from the previously created table. And this time, instead of just providing the PetChip ID, I also try to query according to the time. Okay, so I provide a time range. And the database is giving me an error. Actually, it's more of a warning than an error. The database is telling me, listen, if you perform this query, it's going to have unpredictable performance. You can override this warning and perform the query anyway by using allow filtering, but you don't get any guarantees for how long it might take. Okay, so to overcome this problem and the one that we saw before, we're going to define a new table. We call it heart rate V2. And in this table, we have the same three columns, PetChip ID, time, and heart rate. However, our primary key has two parts. PetChip ID is the partition key, just like before, and time is the clustering key. Okay, so if you remember the chart that I showed you before, we would have, let me show you again. We would have, for a given partition, we would have the time and the heart rate, and we can have more than one value, and they would be sorted according to the clustering key, which is time. So now I'm going to insert some data into my newly created table, heart rate V2, and now when I perform the same query, querying according to the PetChip ID and the time range, I see that I don't get a warning and I get my values. And not only that, but for the same PetChip ID, we have different heart rate values. Okay, now this is a very small table. It has just a few rows. But if you're interested in the performance, you can play around with it and create a very large table and see that this query runs very, very fast, as opposed to running a query with allow filtering, which does a full table scan and can take much longer. Okay, so there are more examples in this lab. I'm not going to have enough time to go over it, but like I said, I'm going to be sharing the link with you so you can run it on your own. Okay, so let's go over a few more slides. I talked about this. Keep in mind that choosing a partition key is very important because the partition key determines how your data is partitioned across the cluster, right? If I go back to this slide with the hash function, is it this one? So if you remember, the database is going to be using the partition key in order to determine where our data will be placed. So it's very important how we choose the partition key, and some considerations or things we would want to do when choosing a partition key is have high cardinality and an even distribution. Okay, so that would mean that we want to have a large set of possible values. Okay, user ID is a good example because there are many different options. Maybe states in the United States is not a great option because there are only 50 states. And that also goes together with even distribution. If we're talking about creating a data model for people in the United States, then not only if we choose states as the partition key will we have a low cardinality, but the data will not be distributed evenly, as we have some big states, say California or Texas, with many people, and we have other states, say Delaware or others that have much less people. Okay, so the data won't be distributed evenly, and that would translate to some nodes having more data than others, and that is not a great utilization of our resources. It would lead to a waste of resources and money, and also bad performance, most likely. Why would we have bad performance? Because some of those nodes, say the nodes that are responsible for California, would be serving probably more requests as they hold more data than the ones holding the data for people, say, in Delaware. Okay, so we want to avoid hot partitions, we want to avoid large partitions, and the best tool for knowing what's happening in your cluster is using the monitoring stack, and this is how the monitoring stack looks like. It allows you to see what's happening with your data, what's the latencies, any errors. You can see if some nodes are working harder than others. And when we get questions from our users, they don't know what's happening in the cluster. The first thing we want to do is have a look at the monitoring stack and see what's happening. Okay, no time for the poll and no time for the drivers. Yeah, maybe just very quickly, we have drivers in different languages. Like I said, Scylla University, you can find an entire course on the different drivers with some examples for how to run each. Some advanced data modeling topics that I'm not going to cover, but just so you know that they exist and you can learn about them in Scylla University or elsewhere. Different ways for denormalizing data, materialized views and secondary indexes. Lightweight transactions are a form of query that allows us to achieve higher consistency levels. Time to live is a way for the database to automatically delete data that's older than a defined time period. Counters, just like they sound, you can increment and decrement. They're a special type of column, and it allows us to perform atomic operations on the counters. And user-defined types, just so you know that all of these exist and you can learn more about them. Next week on Thursday, I believe, the 29th, we're hosting a training event called ScyllaDB University Live. There are going to be 2 tracks, one for beginners, one is more advanced. The event is online and it's completely free, and you can register. Let me paste the link in the chat window, and I'll also send it to you in the email that we send you. Okay, so you can join this event and go more in depth into different topics that I did have time to cover today. Other useful resources, I mentioned Scylla University. We have a community forum where you can ask questions, ask about your specific use case, just say hello, learn from what others are doing, and so on. And with ScyllaDB Cloud, you can, with just a few clicks, start your own cluster and play around with ScyllaDB. That's pretty much all we have time for today. Like I said, I'll be sending you an email with the slides and with some links for the labs and for other stuff. This is my email. It's guy@scylladb.com. Feel free to say hello by email on the forum. And thanks for joining today. I hope you learned something.